Swayam Prabha. Digital India. Educated India.
Okay, so let's continue our discussions related to operational amplifier circuits. And in the last lecture, we have seen that there are many interesting things we can do with op-amps. And the ideal op-amp, meaning an op-amp with very high open loop gain and very high input resistance, an ideal op-amp under negative feedback has these two interesting properties: that the voltage at the inverting and non-inverting terminals are equal, V1 equal to V2, and the currents going into the op-amp I1 and I2 are zero here. And the other property of the op-amp is that the output resistance, the resistance looking into the op-amp here, is very low, and therefore we can connect two blocks of circuits, and the properties of the block, especially the preceding block, is not affected by the block that is connected to it. So there is no loading. So whatever is V01, let's say when the second block is not connected to it, it remains the same value when we connect this particular block to it. Okay, so that's because of very low output resistance of this particular block here. So we can freely connect one block to the next block without bothering about any alteration in the properties of any of the blocks that are there. And so operational amplifier is called an operational amplifier because we can perform a number of mathematical operations using it. So in the last lecture, we had seen that we can perform addition and subtraction. So in this particular circuit, for example, when you apply a signal here, so V0 is, so we can write the result of this particular circuit using superposition theorem. So the effect of VS1, so you remove VS2, remove VS3, remove VS4, meaning short each one of them. And then the circuit practically becomes like an inverting amplifier. So V0 is minus RF by R1 VS1. And similarly, we can write down the contribution due to VS2 we had seen earlier, due to VS3 and VS4 here. And so if we are adding up these voltages, VS3 and VS4, we are subtracting VS1 and VS2. So this is what we call as an adder-subtractor block here. And we can add more segments if we want more terms here. Let's say there was another term which was also negative. We can add another segment here. And similarly, we can add another segment here. So it's a very general adder-subtractor block. We can do more interesting operations. So let's do an integration here. So for that, we have to include a capacitor here. So let's look at this particular circuit. So as usual, this node will be ground, virtual ground here. So the current that is flowing is Vs by R. And the current has no path except to flow through the capacitor here. So this current flows through the capacitor here. And then we write down the equation of the capacitor. So the current I equal to C dV by dt, except that V is 0 minus V naught here. So that's where the negative sign is. And we can rearrange this particular equation as V naught equal to minus 1 by RC integral VST here. So whatever is the voltage we apply here, we'll get an integral of that particular voltage at this output node here. And multiplied, of course, with a constant 1 over RC here. So we can build integrators. So if we have a square wave here, we can integrate it to get a triangular wave here. All right, so we can integrate, we can differentiate also. All that it requires is a shifting of capacitor here. So the current through the capacitor, note that again this is 0 here, so this is C dVs by dt here, so that's the current, the same current flows here. And then we write the Ohm's law. So minus V naught by R equal to the current in terms of V naught is minus V naught by R, C dVs by dt here. And so V naught T equal to, we rearrange it, minus RC dV by dt here. So we get a differential of the input signal here, multiplied by this constant RC here. And since we are applying the signal here to the negative terminal, we get a minus sign here. Inverting terminal will always give us a minus sign that is there here. So we can build differentiators also. Well, we can take a log of a signal. So for that, we use a diode because it has an exponential characteristics. So if we use a diode here, so diode, we assume that the characteristics is I equal to Is, e to the power V by Vt minus 1. So ideal diode with an ideality factor of 1. And so once again, the current here is Vs by R. The same current flows through here. And then we use the diode equation. Vs by R equal to is e to the power v by vt minus 1 here. So we use the diode equation and then we rearrange it. So we get minus v naught equal to, note that it is because of the forward bias voltage is minus v naught. So that's where minus sign is. So minus v naught is vt ln 1 plus vs by ris here. The saturation current is pretty small here. So this factor r times is will be much smaller than vs under typical conditions. So we neglect 1. And so we get vt multiplied by ln vn vs by ris here. So ris is a constant. So what we are able to get is an output voltage which is a log of the input voltage here. Of course multiplied by some constants and there are other things that are there. So we can build a log amplifier here. Let's look at one application. So log amplifier, we also see that V0 is Vt. So Vt is a temperature dependent term. So can we build a temperature sensor using it? So we have the circuit here. V0 is minus Vt ln Vs by Ris here. Vt is Boltzmann constant, temperature, absolute temperature divided by Q. And the trouble with this particular equation directly using it is there's not just temperature dependence here, but there's a temperature dependence in Is also. The saturation current of the diode also depends significantly on the temperature here. So what we can do is we can cancel this effect of Is here by building another. So suppose we change the resistor R2 here, we'll get an output which is V0 is minus Vt multiplied by ln Vs by R2 Is here. And if we take the difference of the two here, then the Is will cancel each other. Okay, so let's look at how we can do here. So this is V01 and this is V02. So we take two identical diodes and the equation here is V01 is minus Vt ln Vs by R1 Is, V02 is minus Vt ln Vs by R2 Is here. And then we would like to take the difference of the two. So we have, this is a adder subtractor block here. So we connect these up here. And the output we get here is Rf by R, Vt ln R2 by R here. And therefore, note that R2 by R1 is a constant, Vt and Rf by R is also a constant. So thereby we get an output voltage which is directly proportional to temperature. So this can act like a good temperature sensor here. Well, if we shift the diode from the feedback loop to the input side, we get a anti-log amplifier, or it can take an exponential of the input voltage here. So once again, we have a diode. Note that we are not going to use a 0.7 volt drop here because 0.7 volt drop is just an approximation. So when you have Vs and 0 here at this end, the current flowing is I equal to Is e to the power Vs by Vt minus 1. The same current flows here. And therefore, we have an Ohm's law here. So minus V0 by R is here. So V0 is minus R times Is e to the power Vs by Vt minus 1. And typically the exponential would be higher than, much larger than 1. So we ignore it. And we get minus R Is e to the power Vs by Vt. All right. So we get a V0 is exponential of the applied voltage here, Vs here. So that's an anti-log amplifier. So the first one was taking log of the input signal. The second one is taking the anti-log of the signal here. Well, we can use both these blocks to build a multiplier. So suppose there are two voltages Vx and Vy. We want to multiply them together. So we take log of Vx. So the idea is we take off log of Vx and log of Vy. We add them up together. So when you add the two logs together, it becomes log of Vx multiplied by Vy. And then we take an anti-log. Okay, so let's do that here. So Vox is minus Vt ln Vx by Ris here. Voy is minus Vt ln Vy by Ris here. So let's subtract. Let's add them up together here. The two voltages, let's add them up together here. So minus minus is being fed into the inverting, so it will become plus here. So it becomes Vt ln Vx by Ris plus ln Vy by Ris. And the two logs, of course, when you do it, then you get ln Vx Vy R square by Is square. Next, what we do is we feed it back into our anti-log here. So this log, if we take an anti-log of it, we get an output which is minus Ris e to the power V01 by Vt here, equal to minus Vx Vy by Ris. All right, so we get an output voltage which is with a negative sign, which we can correct by adding other blocks here. So we get an output voltage which is a product of the two input voltages here, Vx and Vy. So we can build multipliers also here. Well, we have a differentiator, we have an integrator. Well, we can solve differential equations also. So suppose we have a very simple differential equation, dy by dt plus y equal to ft here. So what we can do is we can write it as y equal to ft minus dy by dt. And then we can use a differentiator block. And if we feed in y, we will get a dy by dt. We just saw that we can build a differentiator, dy by dt. And then let's put a subtractor here. So ft, and if we have a subtractor block, so we'll get output which is ft minus dy by dt here. And note that y equal to ft minus dy by dt. So basically it means, what do we do next? Well, we use this equation here, right? Where do we get y from? We use this equation here and we connect them up here, right? So now if we set it up and we leave it, the output of this y here that you get, or the signal that you get here, would be the solution of this particular differential equation given any particular excitation that is given over here. All right, so using this we can solve second order differential equations also, so that's also possible here. Now normally integrators are preferred over differentiators, because in differentiation any small non-ideality, any noise will get differentiated and will have a significant effect on the circuit. So we can rewrite this particular equation as follows: dy by dt equal to ft minus y, and so we can write it in integral form, y equal to integral ft minus y dt here. And then, right, so we take ft minus y here, we apply ft, we apply y here, so we get ft minus y, subtractor. Then we build an integrator, so we get ft minus y. And this whole thing is equal to y here, so we connect it back to the input here. So we can, so this uses an integrator rather than a differentiator, so it's more robust against any noise or non-idealities in the circuit that is there here. All right, so far we've used op-amp under closed loop condition and negative feedback. Op-amps under open loop condition are also useful. And one of the block is a comparator block. Whenever you want to compare two voltages, you can use an op-amp or slightly modified op-amp to compare the two voltages. So if we use an op-amp like this, and Vs1 we feed in the inverting and Vs2 in the non-inverting. So note that the op-amp's internal circuit can be modeled in terms of this, that it has an input resistance Ri and very high gain and very low output resistance, right? So if Vs1 is greater than Vs2, if Vs1 is greater than Vs2, so Vi will be positive, which means that this will be a large negative voltage here, and then the op-amp will saturate to the negative supply voltage here. Right, so if Vs1 is greater than Vs2, output will be, V0 will be equal to minus Vcc. On the other hand, if Vs1 is less than Vs2, Vi will be negative, this term will be positive, and the op-amp will saturate to positive supply voltage. All right, so Vs2 minus Vs1, this is how the circuit would look like here. Right, so if Vs2 is greater than Vs1, then this is negative, and the output will saturate here to the positive value. So this is what we call as a comparator. We are comparing the two voltages Vs2 and Vs1. And the moment Vs2 becomes a little larger than Vs1, note that Vs2 has to exceed Vs1 maybe in a few microvolts. And the moment Vs2 exceeds Vs1 by a few microvolts, because of the very high gain, the output will saturate here. And by looking at the output, you can immediately tell if Vs1 is larger than Vs2 or Vs2 is larger than Vs1. And so, for example, if we have 5.5 here and 5 here, well, what is going to be the output voltage? So 5.5 is greater than 5. So effective voltage here, negative voltage is larger here, and therefore the output is going to be minus 12. It will saturate to the negative supply voltage. On the other hand, if we apply 5 millivolts here, well, it will saturate to the positive supply voltage. So let's look at a application of a comparator. So suppose we have a sinusoid and this circuit is acting like a comparator. We feed into this particular non-inverting terminal here. And this one we can recognize as an integrator. So the output voltage is going to be plus 5 the moment V in becomes greater than 0 and minus 5 when V in less than 0 here. Why plus 5 and minus 5? Because the supply voltages are plus 5 and minus 5. So if we have a sinusoid like this here, 1 volt, the output of the first stage here is going to be 5, then minus 5. The moment the sinusoid goes negative, it goes to minus 5. And so we've taken a sinusoid and converted into a square wave here. And this square wave is being fed into a integrator. So what we'll get is a triangular wave here. So you can see a waveform converter circuit here. You can go from sinusoid to square to a triangular waveform here. All right, so there are many other useful applications of op-amp circuits, and that's why the name of this particular block, operational amplifiers. You can add and subtract, you can take log, you can take anti-log, you can differentiate, you can integrate, and you can even solve differential equations. Okay, so let's stop here.